So welcome. So this is the first video on the Gauss's law section. So Gauss was a mathematician, but he's really well known for this bit in physics. In principle, what we do is we draw one of those diagrams just like we did in lab. So we have our positive and we have a negative, and it's not always as simple as that. You know, it doesn't matter. But let's do a negative line. So whatever, you know. And what you find is that with a bit of practice, you get to the stage where you know that field line goes like that, and you can guess that one goes like that. You can guess that one goes like that. And you can guess there's one going to be around here goes like that. And one going to be around here goes like that, and then one going to be around here goes like that, and then one going to be around here goes like that. And you can even get one that goes way around there, and you get one that goes way around there. And then, okay, so, and they're kind of useful. This is where a positive charge would flow if you let it go. It goes away from the positive towards the negative. And then let's say you get a bit picky. And you go, well, you know, I'm a A-type person, so I'll only do one half of it so you can see the contrast. And then you go, well, you know, I can even do that. You're joking. And what you notice is that especially the more you put in, the more you see this gradation of density of lines. And really the insight that Gauss had was that he recognized that the density of lines is an indication of the electric field strength. Electric field line is just a line showing which way a positive charge would go. But when you get a lot of lines together, it means it's a strong field at that point. If I had a needle, what happens is the positive charges tend to amass near the point, and they don't like to be near the flat bits. And what you find is the electric field lines spew out of there. And so there's a very strong electric field in that region. So he said, you know what we could do? We could actually just take a loop, and we could characterize the strength of the electric field by saying how many of these lines go through. So that's a not very strong region of electric field, and the other one's a very strong region of electric field. And it works. So let's think about it. He's drawing an abstract diagram of an abstract concept, and he's doing math on it. And he's getting useful answers that numerically are correct. I mean, it's like, this is the idea about that model. We have a model, and the model doesn't have to be literally true. It just has to have the right physical parameters, the right characteristics, so it behaves like the real thing behaves, you know. I mean, we do it all the time. You know, things are not, you know, if you're at the airport and you see this thing, like it goes like that, you don't go around and say, oh, I've got a backpack, you know. I've got to go somewhere else because my bag doesn't look like that bag, you know. You know, it's baggage claim. Baggage claim is over there. So we generalize, and we use symbolism an awful lot without realizing it. But when we can do math on something like that, that's like amazing. And so that's what he did. So we invent this term, a new piece of vocabulary, electric flux. Electric flux in a uniform electric field. We'll talk about that. Uniform fields. We'll talk about non-uniform fields. We'll talk about closed surfaces, and we'll talk about Gauss's law. And then we'll go on and play, and we'll get to these other bits later on. We'll get to those later on. So what is electric flux? Imagine that the lines, the arrows, the electric field lines really existed. Imagine you could look at your plate of charge and you could see the arrows coming out. The electric flux is basically the number of arrows. So how many arrows do you imagine coming out of this thing? So here I have a uniform field. I can tell. How do I know that that is a uniform field? What is the giveaway? These are arrows of electric field lines. So these are field lines, E field lines. So how do I know that that is a uniform field? Well, not just they're all. I mean, there's something about they're all describe to me their orientation in terms of math terms. The parallel, yeah. If you these are not parallel. These are diverging and converging and all that. These are nice and parallel. That's a uniform field. So it's a uniform field. Imagine a surface. Imagine an imaginary surface. You can imagine putting a card there. But it's an imaginary surface that is perpendicular to the field direction. So you know that's 90 degrees. We're putting an imaginary card into a flux of imaginary field lines. But we're saying it's got to be at 90 degrees. The electric field arrow density, that's the number of field lines per square meter, is proportional to the field strength. If it's a stronger field, they'll be close together. If it's a weaker field, they'll be farther apart. The product of the magnitude of the electric field and the surface area is called the flux. So this is my electric field in newtons per coulomb, and this is my area in meters squared. So this is my flux. So the flux is in newtons per coulomb meters squared. That's my flux. And it is indicated by the number of arrows. Electric flux is proportional to the number of electric field lines penetrating that card. It's not necessarily one-to-one, but we'll get to that later. But the more arrows you imagine going in, the bigger the flux. The bigger the flux, the more arrows going in. Supposing that by circumstances I just don't have the card 90 degrees to the flux lines. What happens then? Well, I've got to take a component of the area. The area is not the same, is it? This is the area that I think my card is, but the area that counts is the area that's like, you know, that cross-sectional area. So I've got to do a bit of trig, and what I realize is that divided by that is the cosine of that angle. Yeah? So that area divided by that area is the cosine of that angle. If the length divided by the length is the cosine of the angle, that area divided by that area is the cosine of the angle. So then I can say, well, my flux is equal to my electric field multiplied by that cross-sectional area, which is the electric field times the original area times the cosine of that angle. And I've seen stuff like this before, a little bit with, do you remember with work, F is equal, so work is equal to FD cosine theta? And I said, well, work is equal to vector F dotted with vector D. Do you remember that from Physics 1? But area is not a vector. Well, look, we just made up a whole bunch of imaginary field lines. We made up a card to go in the field line, so I think we can make up a vector. So we invent this thing called the area vector. And the area vector is at 90 degrees to the area, and it has a magnitude equal to the area. So now, if I look at this, I can say, oh, my flux is equal to the electric field strength multiplied, dotted with the area vector. Yep. If the area is 4 square meters, that would be 4 meters squared, and it's in that direction. If it was 1.7 square meters, it would be 0.17 square meters. It would be 1.7 square meters in that direction. Now, with surfaces, it's always is at the top surface or the bottom surface. And we'll get to that in a minute. At the moment, we're just going to say it's the surface, it's the area. But is it the top of the area or the bottom of the area? We'll figure that out in a minute. Yes?
Units the same?
Units to what?
The B for this one? It's units for units.
Oh, yeah, flux is always, because it's just, it's the same thing multiplied by cosine of an angle. That's just a ratio. That's just a fractional thing less than 1. So, yeah, same units. Good. So electric field of 2 newtons per coulomb points in the positive x direction. So there's my E, and that equals 2 newtons per coulomb. What is the electric flux that passes through a 3 square meter card that is in the YZ plane? So let's just draw that. There's my card. Because in physics, of course, this is x, and this is y, and this is z. Okay, so this is just a visualization, thing. I have my flux lines coming through. I say my flux is equal to, and we might as well just learn it. It's E dotted with A, which equals the magnitude of E times the magnitude of A times the cosine of the angle between them. And I look at my diagram and I say, well, this is 2. And that guy there, that area there is 3 square meters. That's 3. And it's the cosine. And there's my, here's my E. And I'm going to show my A there. There's my A. So there's my E. And there's my A. And what's the angle between them? 0, isn't it? Because it's like they're parallel to each other. So that's 0. So I is equal to 6 newtons per coulomb meter squared. It feels very uncomfortable, I think, when you first begin, but it just gets to the stage where you just got a whole bunch of new things to think about. It's actually one of these things where the more you use the area vector, the more it becomes just abstract math, so it gets a bit easier, there's less visualization. Cool? An electric field of 7 newtons per coulomb points in the positive x direction. What is the electric flux through a surface that is 2 square meters if the normal to the surface is inclined at 70 degrees elevation above the positive x-axis while being in the xy plane? Oh my word. This is why diagrams are so good. 70. This is 2 meters squared. Let's call this my A. Let's call this my E. So this is my, Y. There's my Z. There's nothing in the Z. That's 70 degrees. I say E, flux, is equal to E dotted with A, which equals E times A times the cosine of the angle between. So my flux is equal to 7 times 2 times the cosine of the angle between them, cosine 70. So my flux is equal to 14 cosine 70. 4.788, 4.79. Agreed? Yeah. What is the, if I said to you, what Greek letter is this? What would you say for that? What Greek letter is that? What would you call it? So most commonly in the American phi, but it's also phi. It's just two ways of saying the same Greek letter. It's good to know the Greek letters. You know, you don't have to know every one of them, but as you learn them, you know, I kind of like was one of these people again where I kind of said, oh man, you know, I don't need that, and so I wouldn't know what to call it. And again, if you know the letters, it's just a bit more professional. I was always raised with it as phi, never as phi. And then a few years ago, I was asking a class what the answer was, and I had this. Everybody said phi. Who spoke? Everybody said phi, apart from one person who said phi. And I kind of glanced. It was an evening class, and I glanced up, and I said to the one voice that said phi, "Well, actually, it's phi." And then I realised he was the only Greek student I'd ever taught in my life, who was an international student. And you know, I said, and just my mind was, he knows more than I. So I said, although you probably know better than I do. And he goes, it's either way. You know, he's very nice about it.
Well, you probably learned Greek like a long time ago, you know, long before he did.
I'm not that old.
I mean, you were speaking Greek before he was.
Hey. Yeah, no. There was this part of me that said, you know, I'm British, you know. I mean, just because he doesn't say it right doesn't mean to say that I'm wrong, you know. There's that colonial kind of like, you know. And then it quickly died, which is why I'm in America. Man, I hope that's not on the tape. Anyway, third one, electric field is given by, oh my word, passes through it, oh my word. What is electric flux? Piece of cake. You know, you don't have to draw it perfectly. There's my E. There's my A. If it makes you feel better, put a little circular card on the end of the A at 90 degrees, so just to remind yourself. Flux is equal to E dotted with A. So my flux is equal to, where's my E? My E is 4I plus 2J plus 3K dotted with my A. My A is 3I plus 4J minus 2K. My flux is equal to, how do we do a dot product? Can you remember? Multiply like. So it's 4 times 3 plus 2 times 4 plus 3 times minus 2. So my flux is equal to 12 plus 8 plus minus 6. So my flux is equal to 20 minus 6 is 14 newtons per coulomb meter squared. So let me ask you a question. So is flux a vector? No, it's not, is it? It's the number of, if you like it, think of it as the number of field lines. We talk about a flux of arrows. We don't necessarily mean the direction they're going in. It's just a whole bunch of arrows. So we think of it like that. Can you see also how there's no attempt to visualize here in real terms? I mean, I put my diagram down because it helps me. But in real terms, it's kind of like, it becomes like quite abstract. So for those people who are don't like to visualize as much, it actually makes what would be a very nasty situation if you had to draw diagrams for it a lot more straightforward. Last little thing, I'm going to just leave you with this, with where we're going. What we're going to do is we're going to start inventing things called Gaussian surfaces, which are closed regions where you have a whole bunch of cards forming a potato shape or a sphere or a cylinder, and they're going to surround charges. And we're going to find out, in fact, that we can invent a thing called Gauss's law, which basically says that the flux passing into or out of a Gaussian surface, which is the integral of all these little EDAs is equal to the charge inside divided by a constant. This is amazing. This means that we can find the electric field if we know the charge and we surround it by a well-behaved Gaussian surface. And that's the skill we're going to develop next time, okay? So, we'll thank you.